If everything goes according to plan, we will soon enter a new era of astronomy. The James Webb Space Telescope, the largest and most expensive and complex space telescope ever built, is now in space and has reached its final destination. The launch of this $10 billion telescope on Christmas Day 2021, anticipated for over a decade, was both exciting and terrifying for the thousands of scientists, engineers, managers, and support staff who brought the mission to this point. However, Webb just detected a very strange light in the universe, which almost changed how scientists look at astronomy and space. So join me as I show you insights on mysterious cosmic light that were finally detected by James Webb Telescope in deep space. Webb has done it. On February 3rd, NASA announced the first particles of light have made their way through the entire telescope. This is the closest scientists have come to their ultimate goal: to use the Webb to image the universe as never before. The achievement was confirmed by the near-infrared camera, one of the science instruments on board, which captured the photons. What exactly is a photon? As quanta of light, photons are the smallest possible packets of electromagnetic energy. Photons are everywhere in particle physics, so you almost forget about them. The photon has fueled centuries of discovery, and it remains an important tool today. This data is critical for the next step towards Webb's science mission and toward getting actual images we on Earth might marvel at too. These near-cam readings enable scientists on the ground to start aligning the telescope's 18 mirrors to form a fresh lens on the cosmos. We had model and computer simulations of what we would see when we pointed at specific places in the sky, and the actual data looks very similar to the simulations, a NASA spokesperson tells Inverse. As part of that process, Webb's mirrors will progressively focus in on HD 84406, a star similar in size and brightness to our Sun that makes up the Big Dipper constellation. The full alignment will take about 3 months, starting now. Webb's primary mirror consists of 18 individual mirror segments that need to work together as a single high-precision optical surface, explain engineers Scott Acton and Chandra Walker of Ball Aerospace and Lee Feinberg of NASA Goddard in a statement. In the announcement, NASA offers a nice analogy for the precision this entire process requires: what first light means for Webb. Confirming that photons can pass into the telescope and show up on its detectors is crucial for the next stage of aligning the 18 beryllium and gold segments that, as a unit, comprise the Webb's mirror. To bring each segment into the right position to work together perfectly, the team need to tweak their individual position by focusing them on the star HD 84406. Any final Webb image will essentially be a stitched-together composite, so when the Webb looks at HD 84406 initially, it will produce 18 slightly different fuzzy pictures of the star. The engineers need to match each picture to the right segment. Once they know what segment is producing what image, more difficult than you might think, then they can move the segments to look at a single point with greater accuracy. After that, they will move on to segment alignment, a stage where each mirror segment is brought in and out of focus to produce 18 in-focus views. Adjustments of the segments then result in 18 well-corrected telescopes, the three engineers explain. However, the segments still don't work together as a single mirror. Once the engineers achieve this goal, they can move on to a phase called image stacking, where each segment image then comes together to produce a unified picture, with all the light falling in one place. But the segments are still acting like 18 telescopes. Getting beyond that issue requires two processes called coarse phasing and fine phasing. These are a bit technical to explain, but together they serve to better line up the segments and make the picture they produce more accurate and clear. Finally, the engineers need to do field of view corrections and final little adjustments to get the segments just right. Of course, the engineers' work will not be over at that point. They will then need to turn to commissioning the different instruments on the Webb. The process is flexible and modular to allow for iteration. After roughly 3 months of aligning the telescope, we will be ready to proceed to commissioning the instruments, the engineers say. Now, there's nothing quite like the moment you switch a brand new gadget on for the very first time. That refreshing ding and an unstained, glowing screen almost feel as productive as doing actual work. If you know what I'm talking about, then you can likely imagine the satisfaction the scientists running the James Webb Space Telescope feel right now. All Webb science instruments are powered on, ready to reveal our cosmos as never before. What's new? Well, on January 31st, NASA revealed via the Webb telescope's Twitter and blog that the telescope's suite of science instruments are now all on, a critical milestone on the road to beginning its era of discovery. This represents the culmination of a weeks-long process that began soon after the Webb launched into space on December 25th, 2021. The first instruments to switch on were the MIRI instrument, or mid-infrared instrument, and certain other parts. Now, NIRCam, or the near-infrared camera, the near-infrared spectrograph, and the fine guidance sensor, near-infrared imager, and slitless spectrograph are all also confirmed to be switched on. All of this is possible because the telescope is now safely stationed at Lagrange 2, a point 1 million miles away from Earth, where gravity keeps the observatory in a stable orbit, far beyond the Moon. The Webb team also turned on the observatory's high-gain antenna on Friday, boosting its communication line with Earth and ensuring the swift return of images and other observations when the time comes. Ultimately, we will still need to wait until the summer to see the fruit of all this labor and many billions of dollars. But in the meantime, we do have some idea of Webb's first targets slowly trickling out. Many of these are, of course, informed by what the main instruments on Webb are capable of. What can Webb's science instruments do? The ultimate goal of the James Webb Space Telescope is to use infrared imaging and other tools to stare deep into space and time. The telescope will reveal new details about the universe in its infancy, perhaps even the first ever stars. At the same time, it will also observe the planets and objects in our own solar system with fresh eyes, heralding an age of new astronomical discovery closer to home, too. It will stare deep into the gassy depths of strange worlds' atmospheres, looking for signs of life, and perhaps even reveal the intimate secrets of distant galaxies never seen before. To do all this, the Webb is kitted out with 4 main instruments: the mid-infrared instrument, the near-infrared camera, the near-infrared spectrograph, and the fine guidance sensor, near-infrared imager, and slitless spectrograph. Here's a very brief breakdown of what they do. The mid-infrared instrument, MIRI, is both a camera and spectrograph. It can see infrared light, which our eyes cannot see. Infrared light can help reveal phenomena like redshift, which can help us understand how galaxies, stars, and planets form and evolve over time. MIRI will be crucial to several Webb science missions, like the quest to discover the first stars and to understand black holes. The near-infrared camera is the telescope's primary imaging tool. It will be the key to science relying on direct imaging, a method of detecting exoplanets around stars and other distant objects. The camera essentially blocks out the target star's light, leaving just the objects around it behind. It may be the source of fresh discoveries of habitable Earth-like planets around nearby stars. The near-infrared spectrograph works similarly to a prism. As light comes into the spectrograph, the instrument separates the light and enables astronomers and astrophysicists to decode what the light has passed through. This is crucial information when it comes to understanding exoplanets' atmospheres and determining whether they hold water. But it won't just tell scientists about exoplanets. The near-infrared spectrograph can reveal chemical information about many different objects in space. FGS NIRIS. This is the fine guidance sensor, a part of which is the near-infrared imager and slitless spectrograph. This is the tool that is key to pointing Webb at precise targets and getting a clear image of the target. Again, it will reveal exoplanets in a new light and help pinpoint the first stars. What's next? Now that it is safely in its parking spot L2 and the instruments are on, it is possible for scientists on Earth to turn the instrument's heaters off. These little radiators were vital to preserving Webb's science suite through the icy conditions of deep space. It would have sucked, if you follow me, to get fog on that proverbial lens. But now, the instruments need to cool down to their ideal operating temperatures. This, NASA says in a recent blog, will take months, and it will lead us to a massive milestone in Webb's setup, focusing its mirrors. Feel free to leave your thoughts and comments down below on the James Webb Telescope and on how this discovery will affect space and astronomy.